Imagine a time when we looked up at the stars and believed the universe was static, a grand, unchanging cosmic clock. Beautiful, yes, but fixed. This was the prevailing wisdom. Then came a man named Edwin Hubble. In the 1920s, he peered through giant telescopes, not just at stars, but at faint, fuzzy patches. These were spiral nebulae, as they were then known. He sought to measure their distances and their speeds. What he found shattered our cosmic view. Hubble discovered something astonishing. These distant nebulae, which he proved were entire galaxies, they were not standing still. So, what does it mean for the universe to expand? It's a tricky concept. Many people imagine galaxies flying through space, like shrapnel from an explosion into a pre-existing void. But that's not quite right. The reality is even more profound. It's space itself that is expanding. The very fabric of the cosmos is stretching. Think of it this way. Imagine a balloon with dots drawn on its surface. As you inflate the balloon, the rubber stretches. The dots move farther apart from each other. Not because they are crawling across the balloon's surface, but because the surface itself is expanding. This is much like what Hubble observed with galaxies. Those galaxies are the dots, and space is the balloon. This expansion is happening everywhere. For decades after Hubble's discovery, astronomers debated the universe's ultimate fate. The expansion was known. But was it slowing down? Gravity, the great cosmic contractor, pulls everything together. So, it stood to reason. The mutual gravitational pull of all matter in the universe should be acting like a brake, slowing the expansion over cosmic time. Scientists set out to measure this deceleration. They used distant standard candles, exploding stars called Type Ia supernovae. These explosions have a known consistent brightness. By measuring how faint they appear, astronomers can calculate their distance, and by measuring their redshift, their recessional speed, this allows us to map the expansion history. This discovery of cosmic acceleration was a bombshell. It meant there had to be something else out there, something overpowering gravity on cosmic scales, something pushing the universe apart, a mysterious repulsive force, or an energy inherent in space itself. Scientists gave this mysterious something a name. They called it dark energy. Dark energy is dark for two reasons. First, it does not interact with light. It doesn't shine, reflect, or absorb light. So, we cannot see it directly with telescopes. Second, its nature is completely unknown. Its presence is inferred only by its gravitational effects, specifically its effect on the expansion of the universe. The biggest question in physics today might just be this: what is dark energy? The simplest and perhaps leading explanation is something called the cosmological constant. This idea dates back to Albert Einstein. He introduced it into his equations of general relativity, initially to allow for a static universe. When Hubble showed the universe was expanding, Einstein reportedly called it his biggest blunder. But perhaps he was onto something after all. The cosmological constant represents the energy of empty space, vacuum energy, as it's sometimes called. Quantum field theory predicts that empty space is not truly empty. It's a seething cauldron of virtual particles constantly popping in and out of existence. This quantum fizz could endow space itself with energy, an energy that would have a repulsive gravitational effect. The discovery of dark energy and its repulsive, accelerating influence has profound implications for the ultimate fate of our universe. If dark energy is a cosmological constant and its density remains, well, constant, then the future looks rather chilly. The universe will continue to expand faster and faster. Galaxies will recede from each other at ever-increasing speeds. Eventually they will cross a cosmic horizon beyond which their light can never reach us. This scenario is often called the Big Freeze or heat death. As the universe expands, its average temperature will drop, stars will eventually burn out. New star formation will cease as gas clouds dissipate. Black holes will slowly evaporate through Hawking radiation over unimaginable timescales. The universe will become a cold, dark, empty place, with isolated particles drifting ever farther apart, a vast, silent, and frigid expanse. But what if dark energy is not constant? What if its density increases over time? This leads to a more dramatic and unsettling possibility known as the Big Rip. If dark energy grows stronger, its repulsive force will eventually overcome all other forces. First, it would tear apart galaxy clusters. Understanding dark energy is a monumental task. It's one of the greatest challenges in modern science. Astronomers and physicists around the world are on the case, employing a variety of ingenious methods and building sophisticated new instruments to probe the history of cosmic expansion and map the large-scale structure of the universe. All in an effort to pin down the properties of this elusive entity. The clues are faint, hidden in the light from distant galaxies and the subtle patterns in the cosmic microwave background. One key strategy is to create even larger, more detailed maps of the distribution of galaxies throughout cosmic history. Projects like the Dark Energy Survey, and upcoming missions like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope, are designed to measure the positions and shapes of billions of galaxies. By studying how galaxy clusters form and evolve, and how light from distant galaxies is bent by gravity, scientists can trace the influence of dark energy over time. Another powerful tool is the study of the cosmic microwave background. The CMB is the afterglow of the Big Bang, a faint radiation filling all of space. Its tiny temperature fluctuations hold secrets about the early universe and its composition. Precise measurements of the CMB by missions like Planck have provided crucial data supporting the dark energy model. Future CMB experiments will refine these measurements, looking for subtle signatures that could reveal more about dark energy or potential modifications to gravity. You might wonder, why pour so much effort, so many resources, into understanding something so abstract, something so remote from our everyday lives as dark energy? The answer lies at the heart of what it means to be human. We are curious creatures. We look up at the sky and we wonder, what is our place in this vast cosmos? How did the universe begin? How will it end? These are fundamental questions that have driven human inquiry for millennia. Understanding dark energy is crucial for fundamental physics. It touches upon our deepest theories of space, time, and matter. If dark energy is vacuum energy, as the cosmological constant suggests, then we need to reconcile quantum mechanics and general relativity. A theory of everything must explain this energy. If dark energy is something else like quintessence, it implies new fields and new forces in nature, waiting to be discovered. And if it's a sign that gravity itself is different on large scales, then Einstein's masterpiece, general relativity, needs an update. This quest could revolutionize our understanding of the laws of nature. Moreover, dark energy dictates the future of our universe. The discovery of the accelerating universe and the inference of dark energy represent one of the most profound shifts in our cosmic view. It's a reminder that the universe is full of surprises. Just when we think we have a handle on things, the cosmos throws us a curveball, revealing new layers of complexity and mystery. This is not a cause for dismay, but for excitement. It means there is still so much more to learn, so much more to discover. We stand at a fascinating juncture in the history of science. Armed with powerful tools and brilliant minds, we are chipping away at the enigma of dark energy. Each new observation, each theoretical insight brings us a little closer to understanding its true nature. This is science in action, a process of questioning, observing, testing, and revising. It's a human endeavor, driven by an insatiable thirst for knowledge, to comprehend the universe we inhabit and our own place within its vast, expanding tapestry. The story of dark energy is far from over. It is an unfolding mystery, one that challenges our most fundamental ideas about the building blocks of reality and the fate of everything. The answers, when they come, will undoubtedly be transformative. They will not only reshape our understanding of cosmology but also our understanding of physics at its most fundamental level.